one second. So this conference that you're about to give, Tom, is falls within the framework of a series of lectures that we've been doing also last year. And you might have seen some last year, I believe, where also Achim Menges and some other people, I think we had 10 people that came by. And so we're constantly talking and discussing about experimentation and experience by experimentation, of course, how it can influence or help the conception of architecture, how it can actually be a tool for developing architecture. And especially in these days, we are talking a lot about the digital influence, but beyond the digital, there's a pure experience on material itself, and that can talk about a new paradigm, maybe even in teaching, but also in research, and even why not? Let's hope so. And if we might believe what our colleagues in China are doing together with Professor Philip Yuan, you can see that even the experience and experimentation is possible on a large scale and real constructed level, and actually bringing the boundaries of construction back to a very interesting level, together with the manufacturing power that is on. So the series goes about this, and my colleague and myself, Mr. Berthier, we are working on this topic with the research lab of Versailles, which is called Le Havre. So for all those that are interested, we also offer PhD positions that can be interesting. And especially we have a fab lab where we can cross your PhD research with a real fab lab. We have connections to other engineering schools that can also work on it together. So that's definitely interesting if you're interested. So don't hesitate to contact us. And we also have it on the level of the master's students. There is a special program on experience and experimentation, where students are writing as a preparation to their final degree, a kind of dissertation that works around experimentation rather than the pure literature studies that would have been done otherwise. So that's what this is all about. So happy to discuss afterwards with everybody, of course, and especially our speaker of the day, Tom Svilans, so second in the row. Maybe not as far yet as Professor Yuan in the experience, but that's also, Philip was quite impressive how far he got already in this very short amount of time, how he built up several things. But nonetheless, Tom is not less impressive in his feats, in that he has been part, so he's now working mainly at CITA, but also works for the IAC in Barcelona and for the UCL Bartlett in London. He has been part of a research effort, which was researched by projects, project-oriented research that gave him the doctor title also, which was a European program between, I believe, 6-7 different universities, which was called the InnoChain, and a very interesting collaboration all over Europe, and with different teachers and manufacturers directly involved into the research. So it's written here, sorry, I wasn't reading everything, but I can read it out loud. So he's an architectural designer, a design consultant and researcher, focusing on the intersection of fabrication, materiality, and emerging technologies. He's a postdoctoral researcher at the CITA, so in Copenhagen, Denmark. And his actual research at the moment is focusing on digital design across the timber value chain, from forestry to construction, and methods of integration of new imaging and information communication technologies in design and fabrication of engineered timber elements. So as I told, Tom has a PhD from the Royal Danish Academy that was done within the framework of InnoChain. And this PhD develops a digitally augmented material practice for the design and manufacture of the large-scale free-form timber structure, which was in close collaboration with a timber or a carpenter from Switzerland called Blumer Lehmann. and some multidisciplinary Scandinavian architecture practice called White Arkitekter. And Tom has presented and published his work internationally on many occasions. And he has taught, presented, or been a guest critic for that matter, at UCL, the AA, the IAC, and the Royal Danish Academy. I've had the pleasure to work with Tom already a couple of times, and it's been a pleasure always, and I'm really much looking forward to what you're going to show us today, Tom, so surprise us.
Okay. Well, thank you very much, Klaas, for the great introduction. It's very thorough as well. So let me just share my screen. We can kick things off. So yeah, I mean, thanks for the invitation. It's a real pleasure to present my work and talk about what we're doing right now at CITA. And today I was going to, I wanted to talk about two things. One is to give a fairly short presentation of my PhD work, which laid the foundation for what I'm doing now, and then continue with some of the current research at CITA into timber, and developing this idea of the digital timber continuum. And just on that note, the digital continuum is a term that was coined by Branko Kolarevich in the sort of early 2000s, when the digital manufacturing and digital fabrication was really taking off, as a way to kind of express this continuity between the model and the finished object, where now instead of making drawings and making models and then making information so that somebody else would make the actual building, we have this opportunity to basically directly inform the machines with our with the data from the models. Yeah. So that's the digital continuum, and we think that if you augment this with a closer look at material, in this case wood, and really take into account what's happening at a material level, and with especially with heterogeneous biological materials like timber and cellulose and fungus and whatever, we can build upon this to have this greater sensitivity to the way we build things, and achieve new insights through the integration of digital technologies in this sort of aspect. So that's those are the two main topics I want to sort of pass on today and talk about. Yes, so CITA, can you all see this? I think my toolbar might be in the way, so I'll just shuffle that to the corner. CITA is the Center for IT, or Information Technology and Architecture. It is, as Klaas mentioned, it's based in Copenhagen in Denmark, at the Royal Academy. And the main focus of CITA is how digital culture impacts the way we design and make objects. So it's this intersection between architecture and digital technologies and material practice. So it's not only the digital, but how does that actually translate into material considerations? And CITA looks at this focus through many different ways. One is through a very active participation in the research community and conferences and publishing work. CITA is very collaborative. We collaborate with all sorts of partners around the world, and big EU projects. And then maybe just as importantly, maybe a little bit more importantly, through building and through making full-scale demonstrators and exhibitions as a way to test ideas and put things into practice. Yeah. Next slide, if it will. Yes. So InnoChain, as Klaas mentioned, was an EU-funded research network that was started in about 2015. And it created 15 PhD positions. It was a consortium of 6 academic institutions. So we had CITA, or the Royal Academy, Royal Danish Academy, the Bartlett School of Architecture, ITK in Stuttgart, IOA in Vienna, KTH in Stockholm, and EAC in Barcelona, and then about 14 to 16 industrial partners, depending on how, the project evolved over those years, but these partners were everything from large architecture firms such as Foster's and White and Big and Hen, to smaller practices like ROK and Cloud9, to engineers, Blumer structure, consultants like design to production, Smith, contractors like Blumer Lehmann, and then others, and including software developers like McNeil, who make Rhino. So that's the kind of framework of the project. And in this project, I was partnered with White and Blumer Lehmann, and this kind of conveniently encapsulated this, or bookended this idea of early stages of design and late stages of design. And the premise of InnoChain, or its goal, was to look at what it defined as the digital design chain, so from design through to production, and criticizing its linearity, so how we design things, we develop them, we engineer them, we construct them, we assemble them, and how that's often in industry, it's a very linear process, and how can we start to disrupt this and find new ways of bringing late information forward in the design process, and kind of introduce circularity and feedback within that process. So for my project, it was very much about how do we embed concerns from timber manufacturing early in the design stage at White. So White is a big architecture practice, multidisciplinary. It's a very different environment from Blumer Lehmann. Blumer Lehmann is a big contractor. They produced a lot of buildings by Shigeru Ban, experts in wood. So they kind of represent the two different ends of that chain. So getting into timber, I think some of the main aspects of the timber industry today that have led to where we are today is the development of structural adhesives. So now we are not, from the early 1900s, we are no longer limited by the size of a log. We can start to compose bigger elements. We can start to control the quality a lot better by taking parts of the log that are more high quality and gluing them together with other high quality elements to make very more predictable timber elements. Whereas before, as you know, trees are very variable. There's lots of knots and fibers go in different directions, so it can be difficult to calculate with. So structural adhesives. The other big factor is the timber industry today is highly automated and highly digitally driven. So on the second picture in the middle, we sometimes when we think of woodworking, we think of romantic images of somebody in this little workshop at the top, with a chisel and sunlight coming through the window. But the reality of industrial timber is very different. So in the middle, you see the CNC machine at Blumer Lehmann, that massive kind of building within a building. It's actually something like a 13-axis CNC machine, which can process glue lambs, that are, I think, 30 meters long. So on that as well, because it's so automated and digitized, there's a strong move towards prefabrication. So if we can make the elements in the factory where we can really control the quality much better and be much more accurate, we can pre-assemble everything in the factory and then just put it on the truck and take it to the site and assemble it. And then the fun thing is it also brings up these new notions of digital craftsmanship. So what does craftsmanship mean in this kind of environment, in the digital, in the industrial? How do we translate these kind of ideas to the current context? And there's different, people have written about that. Fabian from Design to Production has written about that. Some others also have talked about how the timber industry and automation and digitization. And in my PhD, I chose to focus on this kind of in-between element. So you have all this sawn wood on the left, sawn lumber after it comes from the sawmill, and you glue it together in this shape, which is usually very close to the kind of the final beam you design. Here we're talking specifically about freeform timber structures. And then you machine it, you cut it with end mills and with saws to kind of take away the surface and really kind of sculpt it to the final piece. So on the right is the finished glue lamp component, which is being assembled into the Swatch building by Shigeru Ban in Switzerland. And on the left is the sawn lumber at Blumer Lehmann next to their sawmill. And in the middle, there's this object, which is called the glue lamp blank. So that's this kind of in-between object between the raw material, or, well, it's actually quite processed lumber, but in between the sort of basic material and the final component. So the question here was, how do we investigate this area And if we look at the bottom, and you have this value chain in the wood from it grows in the forest, it goes to the sawmill, it is laminated, it is processed or kind of machined, manufactured, then it gets assembled and maintained and disposed of at the end of its life. So how could we kind of expand the role of design to go one step backwards, not just in controlling the shape of the final piece, but looking if there are any opportunities in this lamination process or in this glue lamp blank. So that was the kind of main question. And the PhD developed that through these three main components. So on the one hand, so if we are highly information and data driven, we need to look at how do we model and how do we represent and encode these parameters, factors, considerations from glue laminated timber into our models. So how can we design models or come up with computing models that are that give us information, useful information about what is actually going on in the glue lamp. Then we also need to look at the materialization, so at the top, which is kind of exploring this design space. So if we start to engage with making, how can we make it differently? How can we challenge the way it's made right now? How can we look at some limitations and see how new technologies can affect the way we make these highly geometrically complex objects? And then the final part of the puzzle is on the bottom right, which is the design implementation. So once we know how to model and represent and draw these things, once we have an idea how to make them, how do we actually integrate them into design projects? So from the PhD, the result was that in the modeling kind of side, it led to the development of tools and workflows and which were eventually turned into plugins and libraries that kept track of a lot of the parameters and lamination sizes and relationships between curvature and geometry and joints into kind of tools that designers could use quite easily, but that nevertheless gave good and important feedback at the beginning of a project to kind of anticipate complications. And on the bottom, it was also a matter of saying, well, wood has all these properties and fiber directions, so how do we see them in a model? So much of the time we can have the same geometry, but there's this extra layer of material information now, and so there need to be modes of representing that, either through color mappings of which represent vectors of grain directions or different visualization techniques there to find out, if you cut across the end grain of the wood, that's very different than if you cut along the grain. There's different implications for durability and strength and so on and so forth. And then in the domain of materialization on the right, we explored different ways of, now that we have these complex forms, which you can't just put on a table or put on a CNC machine just like that, how do we actually deal with them and how do we actually keep track of what is going on during production? So we looked at different ways of integrating 3D scanning and motion tracking and LiDAR scanning into the process. So how do we connect the digital model to the actual physical thing that's being produced to make it possible to, or easier to produce it more accurately? And then also on the making side, it was looking at, glue lamps are usually made by cutting lumber into strips and then gluing it together and then maybe bending it and then machining it, and then that's it. Whoops, let's get rid of that. And then the question here was, well, there's all these processes within that value chain. What if we just thought of some slightly different ways that we could do things? For example, on the right, what if we glued together small offcuts or small pieces in the rough form that we needed? So using some of the waste from other processes, and it's just much easier to glue and deal with straight, short elements. Then using our digital fabrication, we can machine the perfect surface from this object. So it's kind of giving the offcuts another life before they are turned into sawdust. And then we use that as the formwork for laminating the continuous fiber along the outsides of the beam. So we have maximum strength on the outsides of the beam where it needs to be, and then the inside is more variable. And then we also use the piece itself as formwork. So it was kind of looking to, what would this look like? And then on the bottom is the result. And on the left, this cross-laminating branching blank was asking, well, in a lot of these highly complex lap joints, you're cutting away half of the beam. And what would happen if when you're making the glue lamp, you put the laminations in layers so that one layer passes through, the other one stops, and vice versa, right? So you kind of interleave the connection, and then the connections are just at the ends, they're end to end, which in some situations might be easier to deal with. Yeah? So it was just trying to challenge or kind of rethink existing ways of making glue lamps and developing some possibilities. Go to the next slide. Yeah, and then that also turned into what happens if a glue lamp splits. What are the implications of that? You get a lot of splitting forces, so you have to laminate in like a cross-laminated layer at that connection, or figure out some way to hold that in. But also, what from a design side, what is the potential of that? What is the spatial potential of that? If now you can have glue lamps that start to split and go off in different directions, it might be an exciting sort of spatial possibility. And then things like what are called the kinky blank is when you have largely straight elements and then only small areas of very tight curvature, where you start to cross-laminate between layers to kind of approximate the form. And the one on the right, I mean, that principle it's used all over, in furniture, for example, for making objects. It's also used in some constructions where the forces aren't as great. But this was trying to kind of formalize that and kind of try to make this family of different types of speculative blanks. Then in the design realm, there were a series of projects that looked at, and so what are the spatial implications now that we have these different types of glue lamps, now that we have this way of working, how can we sort of push the spatial aspect of it, and how can we also stress test the tools and the techniques on more architecture projects. So on the left there was the entry for the 2017 Tallinn Architecture Biennale, where we just kind of wanted to push it as far as we could. And although the rendering looks like a big bowl of noodles and it's super complex and crazy, but the key thing there was that we had a grasp of every single piece within that through the kind of the modeling framework, and that was what helped to convince the jury at least to give us second place. Because you had, on the one hand, you had this massive complexity, but then we could also show that we had graphs and other ways of representing and managing this complexity, and by connecting the overall design to each and every glue lamp, and then also every glue lamp blank. And so even in this complexity, we could know exactly what's going on with each member and how much, what is the thickness of wood we would need to make those curvatures and so on and so forth. And then on the right, it was a project for a pedestrian bridge that started off as a concrete bridge. And this was when I was working with White, with Jonas in Stockholm. And what we tried to do was make a case for making it out of timber. So that was actually a really good opportunity to look at the very early stages of design. It kind of existed as a line in a site model as part of a much bigger project, right? So there was no information about the project, very early stage, and that was a good opportunity to try to integrate these techniques and kind of build a case to convince the project team, the client, the engineers that making it out of timber would be a good idea. So it has this form because it needs to have a certain slope, and therefore it needs to have a certain length because the one end is higher, and there's not much horizontal room. So it kind of ended up being this kind of question mark that looped around and came down. And although it is very curvy, and a lot of the elements that were designed were double curved, then we made this exercise where we said, well, by knowing how it could be made, by knowing the different types of glue lamp blanks, we could actually make it much more feasible and manageable, just by kind of mapping this, just with this awareness and kind of looking at how with small changes just in the glue lamp blank, we can keep the design geometry, but have a much more savings in the complexity of fabrication. So that was just the game there was let's not change the design geometry. Let's see how just by changing the types of glue lamps we use and the material composition, how can we lower the complexity and therefore lower the risk. And both of those projects were we wrote about them and published them. So And then following this was the kind of final model for my PhD, which took the design of this bridge and kept all the complexity. And then this was a test of saying, okay, now I've got these modeling tools and workflows. I've got these, 3D scanning and making kind of workflows and methods. How do we now try to integrate all of this into one workflow and kind of demonstrate that it can be done? And also, this kind of took a small section from that bridge and kept the high curvature and complexity, and then I went through an exercise of making it. So gluing all the blanks, which you see up top here, putting them on a 5-axis machine. So on the bottom, you can see the 3D scan of the machine and where the piece is, and how we use the 3D scan to align this kind of non-orientable geometry. And then you see the 5-axis machine starting to cut some away, and then on the right is the result. And I'll admit there was supposed to be a third leg, but I ran out of time, and it had to be put in a box and shipped to Copenhagen to be exhibited. But that was the kind of result of that. So the outcome of that was, well, as I mentioned before, the PhD was about developing this as a material practice. So saying, well, now what is a digitally augmented material practice in timber and in freeform structures? So, it has to take into account, it has to kind of live between design, manufacturing, and if it's augmented by digital technologies, then those play a strong role. So the contribution was sort of proposing this new way of riding somewhere between architecture and manufacturing and bridging the gaps in between. That was the kind of outcome of that. Okay. So after the PhD, as I mentioned at the beginning of the PhD, the goal was to see how we could extend the scope of design into further back into the value chain, into lamination and manufacturing. And then the question was, well, how can we go back even further? So what happens in the sawmill? What happens in the forest? What are some interesting developments here? And we find that today in forestry and sawmilling, these things are incredibly advanced and very digitized as well. There's all this information, all this technology. On the left, you have Treemetrics, which is an Irish company, and they developed this idea called Internet of Trees, where they work with forest owners, and they go out with the trucks and the harvesters, and they're constantly 3D scanning the forest. So they're keeping track of how the trees are growing, and they know exactly which trees will almost be ready to cut down. So through and they use satellites to map out, what is the status of the forest, and where it can be harvested, where it should be left to grow a bit more, and how to be just more sensitive, more surgical in harvesting. And the really interesting thing here is that basically the guy that is driving the harvester, in the morning, he gets this sort of digital shopping list, tree number, blah, 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 tree number, XYZ. And he just goes out with GPS on the truck and 3D scans to the specific tree in the forest, cuts that down and brings it out and ships it to the sawmill, right? So that's really interesting. So there's all this development happening here. And then on the right, you have this company called Microtech. And it's not the only company in this area, but it's one of the main ones. And they do CT scans. They develop CT scanning technology in sawmills. The immediate benefits are obvious. If you see what's happening inside of a log before you cut it, you can change the way you cut it to maximize the value that you extract from the log. But this also means that all of a sudden we have this rich data set of the interior properties of a tree before even the log is cut down. But before cutting up the log, we already know what we can find inside, where the knots are, what is the density on the inside, and different parts between the heartwood and the sapwood, and so on and so forth. And they've also developed this kind of idea of the digital, or what's called the timber fingerprint, where by scanning a timber element, kind of like our fingerprints, they can associate it to a specific log and therefore a specific tree. So this idea of kind of tracking the material through its whole life cycle becomes possible. So on this side, we in this way of thinking, we developed this project that we call RawLAM, and it's obviously based on glulam, but it uses this technology and this data to ask, well, how does that change? How can that change design, or how can we start to put this into our designs, or how can we start to engage with these all of these data sets and all of this information that is there? And the one way was, well, now if we design something like a beam or a column, and we see that there are it doesn't always behave uniformly. You'll have more stresses and more forces in different parts of the beam, especially when you have something that's bending, because you have to factor in the bending, and with joints, you need different quality. You need high quality material around joints so that you can have very strong connections. How can we start to map these qualities into our designs, and therefore have this kind of hyper specification of material performance and high resolution grading of the material, and in our design elements? Because as you probably know, you can get different grades of material, but it's usually like this board is this grade and that board is that grade. But here, what we are curious about is, could we say in a board, could we say that this part here is this grade, and this other part on the same board is that grade? And by having this kind of higher resolution, how can we start to marry that to the design performance demands that we get from simulation, from calculation, and so on and so forth? So again, as I was explaining, it starts at the sawmill, and then on the left, on the right, this is the kind of data that comes out, right? So these are just slices through the volume of the data, just looking at the differing densities, and you can see the knots, you can see where the pith is, and you can very dramatically see the difference between heartwood and sapwood. And so we set out to try to make something that would express this idea, going from the log and the CT scan at the top here, identifying where are the knots, where are the different parts of the log that we should allocate to different parts of these elements. We just drew a very simple kind of tripod structure just to create some curvature and some different scales and different sort of joining conditions. And then we mapped the demands on this object. So where it curves, we need higher quality material. On the outsides of the beams, we want higher quality. On the insides, it's fine if the quality is not as great, because in principle there's less work happening in the material. And then also, as I said before, the closeness to the joints. So around the joints, we want high quality material. So when we combine all these different mappings, we get this combined map of demands. And then we look at the log and we say, well, it's not about just using the best material, but it's saying, where can we use low quality material? Where can we expose things like the wane and worse parts of the log? And where do we have to use high quality, right? So it's not just about it's not about extracting the highest possible quality from the log, but it's rather saying, can we sort of start to negotiate between what's available and what we need? And we don't want to use high quality material in an area that just needs low quality material, for example, right? So that's the story. Then it also, as the bottom left image shows, it also led us to wonder, well, it might also have a different expression, texturally or spatially or aesthetically, when we start revealing the rawness of the wood and integrating that into the design, which we can do once we have the CT scan, and we can start to be very precise about which part of the log we put where. And that leads to maybe a not super polished, clean timber language, but maybe something that's maybe a bit more rustic, a bit more haptic, tactile, and so on and so forth. And I think this image is really important, or both these are. On the left is now, what that means is also we can take digital geometries and kind of intersect them with the digital log, right? So we have this digital timber in the form of the CT scan, and we can kind of digitally chop it up and then see what the digital boards we have are after, right? On the left is just us playing, just putting different kind of intersection volumes through the log, and then we can kind of see the result of what that would, what that actually looks like once it's cut in that way. The bottom one is just silly. It's just taking some of these kind of beam geometries and just intersecting them, just to kind of, again, find out, what happens when you start to kind of move through a log in kind of funny ways. The right image is also very important, because it's one thing to have all this data and all this information, and then you have the log that's delivered, and then how do you actually link the two, right? So how do you track all of these things through all of these different processes of fabrication? And that's, I think, probably the trickiest part right now, is keeping that link alive, right? Keeping the precision that you have in the model through all the way to the execution. And I'll show that in the next series of images after this, with a very recent project that highlights the importance of this. But here you see, we use a laser projector to kind of show where the knots are, so we can align the board according to its kind of knot fingerprint on the CNC bed, and then do some cuts in there. But I think this combination of images is probably the most descriptive in this series, because on the one hand, now we have this kind of freedom to really explore the insides of the log, and how we can kind of carve it, or cut it up, or whatever. And on the right, it's the importance of keeping that link. How do we maintain our grasp of the material in our hands and the digital material in the computer? And that just resulted in kind of another version of the same sort of tripod, which was just trying to improve on the process and integrate more scanning, and try to get a little bit more precise and tighten the tolerances. So, am I okay on time so far? Should be. Okay. I just want to.
Yeah.
Perfect. So the reason I probably sound quite tired is because I'm in Umeå, which is 13 hours north of Copenhagen, where we just finished installing this yesterday. And this is kind of this is for an exhibition here in Umeå called Architectures of Transition. And it's the next sort of step in this project. And it's about scaling up and also just trying to tighten the information links. And whereas these other previous projects just had one log to deal with, this has 4 logs, and 4 very different logs that we had to deal with. So it's about trying to kind of grow the complexity and see what else we can, see how can we push it to the next level. So we drove up on Sunday and we installed it yesterday, and then now it's sitting upstairs in the gallery space. So this is what arrived at CITA. This was cut, sawn. Before it was sawn, it was CT scanned, and then they sent us the data, and they sent us also the cutting pattern. So we had a kind of an image of a cross section of the CT scan data, and then lines that showed, this is where we cut the log. And then they delivered the cut logs or the boards to us, right? So this arrived at CITA, and these are the 4 logs that were used. These are just kind of slices from the CT scan close to the beginning. So these black dots are actually where, in the sawmill, they drill holes into the end of the log so that they can see them in the CT scan, and they can also see them physically. So that's how they kind of match up. That's how they kind of register the two together. But you see they're quite different. They're different in diameter. They're different. The ones, the one on the top left and the bottom right, I think they had a lot of knots. The one on the top right barely had any knots. The one on the bottom left, I think, was just a worse quality. It had been sitting outside for a long time, and it was just a very variable quality throughout. So we had these kind of different characters. Then we had this design, which was, again, just trying to scale our little tripod into something that stood. So it's kind of starting to get legs, starting to become a structure. It's not a building yet, it's not holding anything super heavy. It's just, at the moment, it's holding itself, but it's just kind of trying to now make something more complex, more parts. So where before we had 3 elements, now there are 13 major elements, a combination of straight and single curved elements. And this image on the left is is the same kind of mapping that we saw earlier. So there's the red means that we have lots of demands in this areas, so mostly around joints, and the green means that there are lower demands. And then on the left or on the right are the two CT scans of two of the logs. So the question is then, how do we take this data on the right and kind of map it onto the left? And this is a drawing that's been drawn by one of our students that's just helping us with the drawings for the exhibition. But on the right, you have all the boards that we received. And then in the boards, you see the individual laminations. And so these are all mapped to different beams. So you have just one part of the structure here, this frame D. So Umeo 1, D1, single curve, straight, and all that. So 5 elements with their connections, and each of them are broken down into the size of lamellas, and then exactly which board and which part of the board those laminations come from. So logistically, it's quite tricky because it involves so much tracking of where is what at what time, and which board has which lamella that goes into which glue lam, and what order do the laminations have to go into the press, and so on and so forth. So it's a bit of mental gymnastics or informational gymnastics, but that's the idea. Then there's a process of cutting them out. So again, using drawings and measurements, and now got a laser projector as well. Then we cut out all the boards. So these are the thick boards we used for the straight elements, and then in the back on the top left, you see the thinner boards that we planed down thinner as well, to have thinner laminations for the curved elements. Stacks of laminations. Each pile is one glue lam. So we have the markings. Each one has D3 is the element, SC is single curve, then 21 is the 21st lamination or lamella in that glue lam. That is the pressing. So we had to build a stronger press, which also needs further improvement. So we steal less clamps from the wood workshop. I think we cleaned out about 70% of the clamps in the school for this, which was quite a lot of fun. And that's when it's not being pressed. That's a formed glue lam still in the press, and in the background you can also see templates, so we could kind of just check the form, and also use that to align it in front of the robot. So this is when it's glued. It's a polyurethane glue that foams when it contacts water, so it expands and kind of makes this mess on the top. But it's kind of beautiful in its own way. Different sort of, it's another rawness that I think is part of the process. And then everything is put in front of our robot with a tiny 6mm bit, just because we don't have anything bigger at the moment, or we don't have more muscles on our robot, so we have to do everything in very tiny pieces and very slowly. And that's all machined. These are some completed elements. We have this big straight element on the top that's about 400 by 1.8 meters with a surface cut into it, so it would sit against another element. And the holes are kind of pre-drilled with the robot, and then on the bottom there's Anagnos keeping an eye on me as I drill those holes deeper for some steel rods to go into. And Tim in the back is checking Facebook to see if it's got any likes. These are some of the drives or photos of the drive from Copenhagen to Umeå. It's holiday photos. It's absolutely beautiful, the lakes and forests and cliffs. And on the right is just as we were entering Umeå at about half an hour past midnight. So it's close to the summer solstice. So here it never really gets dark. But it's a pretty amazing northern landscape here. This was yesterday in the gallery, where we started pre-assembling these pieces. So connecting the straight elements to the first single curved elements and connecting them in chunks so that we would be able to assemble them easier with the gallery staff. And this is Jack, also from CITA, who drove up with me to help. And here he is assembling one of these legs that's split together. So it's kind of, there's a surface that's machined off between each leg, so they fit together. There are two or three steel rods so that they are positioned correctly, and then it's pulled together with some very long wood screws that are about 200 millimeters long. So here are two of the legs, kind of good to go. That's the A0, and this one is the C0. This is the what we call the fatty, because it was the fat glulam, and the big one, which was very challenging just to manipulate, and also it took a very long time for our little robot to machine it, but we got there in the end. And what I liked is while we were setting up is the pieces themselves, like individually, they're interesting by themselves as well as objects, you know, as little assemblies of kind of parts, because here you don't know where it's, you know, what it's part of, but it kind of hints at, you know, something. It's kind of by itself, these volumes are quite interesting, even with small curvatures and quite simple cuts. I think they can be quite interesting objects. But here we see the metal rods in the ends of this kind of pre-assembled component. That goes into this really thick glulam. And in the middle there are pins as well to align these two, because these are basically sit on top of each other, and then they're kind of connected to the big beam. And then they diverge into the legs. Okay. So this is us supporting the big leg with the split and then attaching the other legs. Just trying to manage that on site. Here you can see also offsets, you know, where just because of, you know, small inconsistencies in the information or misreadings, you know, this is because one of the values was rounded to a millimeter. We ended up with 2 extra laminations that made the section thicker, where because each lamination had to be, I think, like 6.5, but we made them 7. But that little distance accumulated into a bigger thickness. So again, just coming back to, you know, having to be so precise and so mindful of every little relationship has been a very tricky aspect of this this project. And then this is the assembled piece. That's Jack looking very happy and relieved that we put it together. Here we're 3D scanning it, and it just kind of looks like this tripod with an extra frame, just kind of expressing the rawness of keeping the wane in the beams, and kind of showing that glue lams don't always have to look super smooth and shiny. They can have a sort of ruggedness and texture to them. And yeah, just some close-ups of some of those joints. So again, you see the offset in the sections, and this is intentional because to deliver this, we could only work with single curved elements, because double curved elements with our current setup at CITA would have been extremely challenging and next to impossible. So we had to kind of break everything down to single curved elements. And then we said, well, okay, they're oversized anyway, so our sections will just, and with our robot, it doesn't care which direction the joints are cut or at what angles. So we can just kind of take that misalignment in the joint. So these kind of bird's mouth cuts they fit together at an angle, so that the sections can start to describe more three-dimensional and doubly curved gestures in space. Yeah? And we kept the corners, no, because just to, you know, not to try to hide it, just to say no, you know, single curved elements connected sort of disjointedly. The laminations change. You see the one up here, it's laminated kind of vertically because it bends to the side, and then this one is laminated horizontally because it's bending down, right? So you have very different expressions between the faces of the glue lams, and then where they meet, you see these transitions. Yeah, and then more close-ups there. Yeah, and then the final thing I just wanted to say, which you know, just the thing that came out of working with all this volumetric data is it's a challenge. It's a challenge to the way that we model things, and especially if we're moving towards a bio-based economy of construction. And in CITA, that's what we're very interested in, where we have projects with cellulose and mycelium. These CT scans present very interesting opportunities. You know, we can understand materials at a very, well, literally a deep level, and see inside of them. But that also kind of challenges the way that we, as architects and designers, model and represent things, because we're so used to this, you know, describing surfaces of things and boundaries of objects. You know? And I think it's an open question, and it's I think something that's important to think about is how can we start to now engage with the heterogeneity of materials and come up with new ways of working or thinking about objects, you know, not as boundaries of inside and outside, but just the change in density or kind of, you know, gradients of change in space, in volume, right? So that's the kind of that's the other sort of parallel wondering that we are doing, that comes out of all this work with timber. That's it for me. I want to thank my sponsors. It's the PhD was funded by the EU, was partnered with Blumer Lehmann and White through InnoChain and the European Commission. Microtech has been helping us with data, and then the last project is here in Umeå at the Bildmuseet. So thank you again for the invitation, and yeah. If there are any questions, or do you want to should we discuss?
I put maybe for those that are interested, of course, the chat is open again, so you're all free to post your questions. So I'm happy to relate that, but that's mostly the easiest way to do it. Firstly, thank you so much for the lecture, Tom. It's always a pleasure, as I said in the beginning, and I'm happy to see. I mean, there are so many things that we should be discussing, probably also for the manufacturing part, for the research part, for the university part in this whole thing, because you're connecting a lot of dots here that are usually working a bit in different fields and not coming closely together. I've been discussing this with my colleagues at the University of Versailles also, but like one of the questions would be to me is how, well, you're a specific specimen, and I think you're Canadian.
Latvian, yeah.
And you're working in Denmark and living in Denmark, doing a PhD partially in Switzerland and at the UCL Bartlett. Yeah. I mean, that makes it already quite a big mix. But where I wanted to get, and I told it yesterday, or we had a little chat about that with Philip somehow, this relation between the manufacturing part and like the industry and academics is something you're really busy with. And that was also the initial thought with European funded research that you had there. And I see in France, there's big efforts to try to promote that too. Maybe you have some feedback on that, because it seems to me, I compare it to the vaccine situation, whereas France at the moment, the vaccines are developed by private companies. There's actually no universities involved. Whereas if you see the UK, you have immediately, or there's very few university level involved. And if you look at the UK, the vaccines are 50-50 private academic, right? So it's maybe a far comparison, but maybe you have some insights on that would be of interest for us, for our research also with Stefan actually.
Yeah, I mean, I completely agree that it's really important to have this relationship with industry. I think for me, my PhD was based on that. I couldn't have done the same stuff I did without those connections, and it was incredibly educational. Like I learned an incredible amount just by working closely with them, and you know, because I think often if in the university you might think of a certain thing or how something is done, and then you go to industry and they say no, like they're like, yeah, in theory that's kind of like that's how it works, but these are all the problems, this is how we deal with it. This is kind of different. You get these kind of different insights into their problems. I think it's really important to engage with them. But I mean, there are also barriers to that, no? And I think one of the biggest ones is incentives for industrial partners to engage in collaborations with universities. You know, sometimes they really like it because it's good PR. Sometimes with a PhD project or some other research project, they will get a very helpful output, you know, something that they can put into practice and use to develop their business. Sometimes there's funds from the EU or subsidies from the government that they can kind of use to that, or they get kind of help from. But it comes down to kind of finding this middle ground, I think, of what is interesting for the company and then what is interesting for the research. And for me and Blumer Lehmann, that was the important part. I wanted to go to their workshop and make glue lamp structures and play with their machines. That was not possible. So we kind of found the common ground of the sensing, because that was something that we could test during one of their productions. That was something that could help them in some cases. And then for the research, that was also interesting. But it took a little bit of dancing. I know that in France, we've been in touch with Simona, who's We got them on board for one EU call once. That didn't go through, unfortunately. But you know, I know there are companies that are very open to those kind of collaborations.
Yeah, there is also help from the state here. I mean, even for research related, so PhDs that can be partially they are helped by funding by the state and a private company. So it's a 50-50 agreement that you do. So I have one running in my office at the moment, and it can be quite interesting indeed, as you say, that it brings a real result actually too, so for the company. So it's really, I mean, and European-wise, we should definitely check into those possibilities over the borders. I think you're a good example of this. And maybe another question is, maybe for the students too, I think that's an interesting fact. Of course, timber is not a homogeneous material, and that's the complexity of it in terms of working with it, in terms of the long-term behavior, in terms of structural behavior in 2 or 3 directions for that matter. So you have to be careful, where do you put your screws, depending on the grain in the timber, of course. And I think this heterogeneity, what you were talking about, is something that is very difficult nowadays to take into account, because we're used to make it one equal sausage, right? But even in the sausage, there's little particles. And I do particularly find this aspect, what you're trying to bring out here, it's quite interesting, because the regulations would never allow for it to go so far as in to just allow for the scans, because even we try to work with full trees as the structural members in a house, but you basically diminish by 20 more or less what the real capacity of that tree would be in a certain way.
Wow.
And because you don't exactly know how many nodes there will be in and how many failures in the tree there are. So I think it's quite interesting how far we could go in individualizing timber structures. Do you think there's a realistic chance that this gets to the normal markets? I mean, it's not about the market, but it's something. How do you see it in relation to the regulations?
A very difficult relationship, because I think the whole purpose of grades is that then you have a table and say, you know, grade 1 can do this, grade 2 can do this, and so engineers then can work with that. I think when you have something like this, it then challenges, then how would you engineer something like this? How would you make that fit into those workflows? And I can see this making engineers' lives incredibly difficult when they have to, all of a sudden it's not just a grade of wood there. It's like, well, there's a bit of grade over here, and then all of a sudden the complexity of the engineering models probably explodes as well. You know? And I think that will always be, I mean, even we work on a couple of small projects in Canada, and even things like getting glue certified is a whole problem, and showstopper in some cases. You know, we wanted to do something out of Akoya, then realized that the glue that they use in the Netherlands is not allowed to be used in Canada. So we had to completely change our approach, and it's just a regulatory thing that completely changes the course of a design. No? With we can show that it is possible, but like physically, technically possible. But there are all these other systems in place, regulations, which for a good reason, for safety, for all these other things, that would take a lot more work. You know, it would be several PhDs to kind of look at how to reform that side of things to accommodate very variable, very kind of specific and tailored wood pieces, for example. You know?
Yeah, but still, I mean, if you look in, as you said in the beginning, I mean, there's a way you said that all these carpenters are digital. We have to be careful, of course, because you talked about one of the best carpenters in the world also. Yeah. And they are surely all quite digitized in the way that they all have circular saws that are completely automated in most of the carpenters' businesses. So there is a certain automation, but not the entire business can do what Blumer Lehmann is doing. So there's a certain automation there. So I think there we have to be a bit careful, like how far can we push it for the others also, that there's a common level. That's part of it, why the regulations work too, because it's accessible to a lot more people. It gives a regular framework in which other people, actually the industry, can work, and even the ones that are less skilled can already work with that. But that tends to be a level or a bar somehow that tends to go down. So actually the knowledge of the really good ones is not, the lower skilled people are not really challenged to get better, because they can, the regulations are a kind of mirror to how good the people in the industry are. So that's one part of it, how I see it. So to break down that, the rule of these regulations, I think that's one part. And there's another part, I believe, that the scanning of timber is actually quite regular, because all the timber that is sawn into pieces in the factories, as you've shown also, it's automatic. It's scanned automatically and put aside the ones that are good enough for certain things automatically. So you could, just by leveling the scanner that is on the head already of the machines, which is a totally automated process with all the sawing mills that we know, they could automatically put it in much more categories and then make a finer mesh of these things and optimize probably the use of timber, which they don't do, because they only have, let's say, 10 categorizations. So they go between 20 and 28 Newton per square millimeter, and that's pretty much it. They could easily have a bigger batch of 40 Newton per square millimeter, which would allow us to use timber in other stuff too, actually.
But also having it's also coming back to this, the grading on a board level. It's kind of, this board is this grade, but if you were to start, even if you were to divide the board into 4 sections and say these 4 sections have different grades, all of a sudden your kind of library or your categorization explodes, because then you have to do all the combinations of the different grades for every part, and then it becomes kind of an organizational sort of nightmare. So it's true. In Gula manufacturing, they have the super high speed scanners for every lamella, and they identify the knots up, they finger join it together. And I think something like this, it would be very difficult to connect with these kind of speeds and expediencies in industry. And like you said, also with the bar or the level and regulations based around that, not everybody has this log CT scanner. They have a lot of these scanners for individual lamellas, but there aren't that many sawmills with log CT scanners. It's still quite niche. But the question is, well, if we want to find where all this data is, there is a lot of data already. There's stuff there are existing processes. And then our question is, can we link it to design? Does it present a value in some ways? And then what does it kind of, what does it stop by? And how can we extract more value? Or if we get to a point and there's a barrier, like, can we get around the barrier? Or is this basically why this shouldn't be the path forward in a way? No?
But maybe to interject there, I think there's an interesting discussion going on now in the field, especially for the future architects here, about the reuse of a lot of elements basically, but also on timber. And so there are startups around Europe now that are amassing timber slats and whatever that they actually get out of buildings, and they're all scanning them. And so it's exactly the same process, I mean, it's a form of timber product that you're going to reuse, but you have to scan it again. So I think there's a real, if I see what you're doing here, and if I see that we would have to go more specific with this reused timber anyway, in a certain way, it all goes hand in hand. So we're, it's again about customization, I guess. Like, how far can you customize this whole thing? And therefore, you need to know the manufacturing part, the experimentation and the experience. And this is rarely done in specific practice. So the architects or the future architects that are listening here, this is the complexity of the game, of course, that we cannot really experience that through when we are building. That we really need the academics also and younger architects to do PhDs and to do research and check and build one-to-one scale to get it into the market somehow.
I think you're exactly right with that. And they're what some of us are, what we're trying to do is define this kind of role. I think having this between academia and industry role is really promising. So run your own practice while also being involved in research. You straddle both worlds. In certain ways, that's what my PhD tried to kind of hint at, was that you need the role of the architect is changing, or it can change if we engage deeper with the manufacturing. We can even things like the design to production. They found a niche where they're sitting between the fabricator and the architect. They're still very digital, very information based, but they found that niche just because it kind of they saw the void and they filled it, and they've had a lot of success doing so. And I think there might be similar niches kind of in between this space of making, prototyping, research, industry. And I'm not sure if it's kind of a jack of all trades idea, but this straddling or integrative role, I think, is really important for architects. Not just we're not just going to draw buildings. We're going to be trying to connect parts of the forest with the client, with the consultant, and say, hey, how about we do this? Why don't we pull these other dots together?
I think, it's amazing that you see how optimistic you see it, and also that use and abuse data of a forest in a certain way. It's still a heterogeneous batch, and people are just seeing it as a forest, but you treat it as a database somehow, and completely digitized. I'm not sure if that's the right way to go about it. I mean, still the carpenter's influence, mostly if they go around in the forest, they know which tree to use actually.
At the scale, at one scale, but when you kind of industrialize it to like millions of trees, then you can't have millions of carpenters walking around the forest. But I completely agree. This is from the perspective of digital. Like, how do we? There's information. There's digital stuff there. How can we explore it from this angle? It's not to say that it's the only or the best one, but it's kind of the focus of. Like, if we follow this line of reasoning, this is kind of where we start to ask. I think there are very many other issues. Even we've been talking to some Swedish partners as well about the issues in forestry, and a lot of it comes down to politics and kind of small landowners with small forests, and then these big companies that own 200 sawmills across Sweden, and there's and the ecologies of it as well. So it's a very multifaceted problem, of which we can only really kind of try to nudge maybe one area a bit, or a couple areas, I think.
Yeah.
Realistic.
No, I think the other discussion is about the laminated timber. I think, the glue is actually still too much having an impact on the ecology. So I think there's some place for debate there too, actually, possibly. But I think it's really very interesting. I mean, the debate, I'd love to see you continue on these things that you're building with this optimistic view of making. And I hope my students, or for the other people that listened in, please follow Tom and his little test. Give him a chance if you have the possibility. And I hope we see you soon back, Tom, on some other stuff, actually.
Yeah, I'd be happy to. It'd be good to hang out and collaborate again.
Yeah, and by the way, I've seen your pavilion in Barcelona last Friday. So.
Okay. Well, and what did you think? Or maybe we say that for another chat.
Yeah, we say that for another chat. It's actually quite okay, so don't worry.
Yeah. Okay. Thanks for having me again. It was really nice to present to you, and good to see you. And I hope everybody enjoyed it. So.
Thank you, Tom.
Thanks, guys.
Take care. And for the other people, tomorrow there's a lecture going to be in French with Jacques Anglade, who's a real expert in timber building. So for those that want to tune in, that's going to be at 12 again. And yeah, thank you for being here, everybody. Take care. Bye. Bye-bye.
Thank you.